This is joint work with Roland, Czerny, Jonas, Juffinger, Fabian, Rauscher, Simone, Franza, and Daniel Gruss. So what is SnailLoad all about? Well, basically it's a remote fingerprinting attack that works without being a person in the middle and without running anything on the system. For example, here we have the results of our open world website fingerprinting experiment, and we were at an accuracy of about 63%. So as we use a network timing side channel, first of all, well, okay, what are side channels in general? Let's stick to the definition of, well, okay, we obtain some metadata and then we derive some data from it. Now, what does it mean for a side channel to be a remote side channel? Actually, remote can mean a lot of different things. So it might be an attack from a different chip. It might be an attack from JavaScript. It might be some network exposed API that's exploited, or it might be local Wi-Fi. So local Wi-Fi is also a little bit of a thing that, well, okay, you still have to be in proximity to the victim. What can be done with that? Yeah, if you have local code execution, you can, for example, fingerprint video. For example, like in the idle leak paper. If you control a local gateway, then you can, of course, precisely monitor the network traffic. It doesn't mean that you are able to decrypt, but you can observe when a packet is sent and how big it is. If you control a Tor gateway, of course, yeah, you can also estimate network traffic. And this has been used for application fingerprinting, website fingerprinting, and video fingerprinting. But now we want to go fully remote without using any person in the middle setting and without using any code on the victim's computer. For that, let's first talk a little bit about internet access technologies. So if you think of your internet connection at home, you might have something like a DSL connection, a fiber to the building or fiber to the home connection, an LTE connection, 5G. All of them vary in throughput, so you might know from your internet provider, yeah, you have a, let's say, 300 megabits per second connection. So the interesting part here is that your internet connection at home is an order of magnitude slower than backbone internet connections, so than backbone connections. So the things that connect the servers to each other, and for example, yeah. So the thing here is, yeah, because of these speed differences or because of these bandwidth differences, there has to be some buffering. This is necessary so that packets aren't lost. So yes, you can imagine it a little bit like this. So you have some high bandwidth segments, and then just before your home, you have a lower bandwidth. And in the idle case, well, okay, it's just, yeah, you get, for example, some TCP packet, you get some TCP packet in, and then your home computer answers with a TCP acknowledgement. In that case, that's the yellow car. Usually it looks more like this, so you get packets from multiple sources, and then also the TCP-X are sent back. If you start playing a YouTube video, for example, well, okay, then in the beginning there are quite a lot of packets sent, and you get back the acknowledgement packet. Your home connection sends back the acknowledgement packets again. So in more technical terms, yeah, if your connection is idle, then the packets sent to you are forwarded immediately. If the connection is busy, there's a slight delay. And there's an extreme case of this, which is called buffer bloat. So if you have really large back pressure on the router. If we ping an external server, for example, and then we open up a website, then depending on the website, we might see a small peak sorry about that. Then we might see a small peak in the round trip times, and if we open up a larger website, then we might see a more visible peak in the site. This also happens if we use another machine connected to the same internet connection. It's almost identical. And this shows, yeah, that we can, or this might already indicate that we can do some website fingerprinting with that. So we basically measured the round trip times for different internet connections while the connection was either idle or a download was running, and basically we were able to observe this difference here for all these connections. If we build an attack on that, yeah, we now have this low bottleneck here, and we have an attacker that's now a benign-looking TCP server, and it is not on the transportation path between, for example, YouTube or the victim's computer. It's completely off path. This allows for multiple scenarios. So, for example, it might be a compromised website. It might be a malicious ad that's delivered to you. It might be an email, spam email or something like that. And there are multiple ways to actually mount these attacks. How does it work? Well, we have our attacker server, which sends out small TCP fragments, small TCP packets. In the idle case, well, okay, there's no delay. Let's skip that because we are a little bit tough on time. But in the busy case, yeah, you see there's congestion on your bottleneck, on your internet connection. And finally, the probe packet from the server is delayed. We then perform some machine learning, and you can get. I have to skip that. The results on that is, yeah, okay, we tested that for 10 videos and also on 10 internet connections. We saw accuracies between 37% on fiber to the building machine, on a fiber to the building connection, and an accuracy of around 98% on a fiber to the home connection. We also did an open world website fingerprinting attack, which I already showed in the beginning. There's more that you can do with that. For example, you can detect whether two people are communicating via video call. So as soon as the video call starts, which you can see here at around 160 seconds, the latency increases. Of course, this like many other side channels, this can be disturbed by noise. So we can, on the left-hand side, we see again website fingerprinting with only 10 websites in that case. On the left-hand side, we have 77% accuracy. But as soon as we introduce noise, for example, in the middle, we have noisy training data and noisy test data. The accuracy goes down to 15%. And if we only have noisy test data, but the training data was not noisy, then we are basically down to random guessing, which would be 10%. The thing here is that SnailLoad is a generic problem of heterogeneous networks. So of networks where we have different throughputs. The thing is that many attacks that previously required a person in the middle scenario or were otherwise restricted in what remote actually means have to be re-evaluated again as in a SnailLoad similar setting. We disclosed this to Google and YouTube, but the problem is, it's a generic problem. So also Google said, well, okay, Google investigated this for several years, but they also concluded that this is a more generic problem and they alone cannot solve it. And with that, I would be up for questions right now.